How do you build a near-perfect computer out of imperfect parts? I'm Tonya Hall for ZDNet and Tech Republic, and joining me is Dr. Steven Girvin. He is a professor of physics and applied physics at Yale University. Welcome, Dr. Girvin.
Thank you. It's a pleasure to be here.
So give us a quick summary on your involvement with quantum computing.
I'm a theoretical physicist. I don't have a laboratory. I work with pencil and paper and computers, but I work very closely with a large experimental team here at Yale. And we're attempting to build a new kind of computer, a quantum computer that uses superconducting electrical circuits cooled down very close to absolute zero in temperature, and operates at microwave frequencies.
You've been involved in researching quantum computing error correction. So how does one build a nearly perfect computer out of imperfect parts? I mean, are we bumping up against the limits of physics?
Error correction is very important both for ordinary computers, which I will refer to as classical computers, and also even more important for quantum computers. Today, ordinary classical hardware is so reliable that programmers don't have to pay much attention to taking care of the errors. They're so rare. They can work at an abstract level where the bits really are 0 and 1, and they don't have to worry about the details of the voltages and currents and frequencies that are actually making the physical representation of the bits. We're not at that stage yet in a quantum computer. The parts are quite imperfect. The number and types of errors that a quantum computer can have are larger and more subtle than in a classical computer. And in some sense, that's the flip side of the exceptional power that a quantum computer has due to the ability to be in superposition states of 0 and 1. That's also the Achilles heel, if you will, of the system. They're very sensitive to small sources of noise, to coupling to the environment, because quantum systems are changed when you or the environment observe them. And we have to find ways for that not to happen in order for the computation to proceed correctly.
So how much processing power overhead, if you will, does error correction create today? I mean, how do you see changes in quantum technology reducing this?
Right now, the way error correction works is there's a hardware overhead. You have to add redundant bits or quantum bits, qubits in the case of a quantum system. And we're in the very earliest stages of being able to even do error correction. It's theoretically possible. There are different proposals, some of which are extremely hardware inefficient and might require hundreds of thousands of physical quantum bits to form one protected logical quantum bit. So right now, that is simply not practical. At Yale, we're pursuing a different approach, in which we have sort of native error correction built in at the lowest level of the hardware, and we use a sort of different approach that doesn't require hundreds of thousands of extra parts. In fact, we're not even using, our quantum bits are not even physical objects. They're not transistors or pieces of electrical circuits. They're literally empty boxes with superconducting walls, and we store tiny amounts of microwave energy in those boxes, individual microwave photons. And that's what holds the quantum information. And it turns out it's possible to encode that information in a way that makes error correction actually relatively simple and actually work.
So is it true that tiny fluctuations in radiation can affect the qubit?
Yes. the quantum states of qubits are very delicate. If there were, they operate at frequencies similar to what your cell phone uses, a few gigahertz. And so we have to shield them very, very carefully from the interference and noise arriving from the outside. Even just the thermal vibrations of the electrons in the wires at room temperature that go down to the very cold area can produce what we call black body radiation, which can really disturb the qubits. So we have to have very careful ways of protecting the quantum computer from all of those noise sources, while at the same time still being able to send signals down to control it. So it's quite an engineering challenge.
It sounds like it. In fact, in many ways, quantum computers of today mimic the vacuum tube computers of the early digital age. I mean, they require large rooms of specialized equipment and lots of support personnel to keep them running. Do you expect to see a Moore's law like future? Do you expect to see like a Moore's law like future for the quantum computers? I mean, even if they never scale down to a laptop or smartphone size?
Yes, so it's unlikely that they'll ever scale down to such a small size, but it's likely and essential that they scale up in the number of qubits, the analog of the number of transistors on a chip. So as you say, right now we're at a very rudimentary stage. The first all-electronic quantum computer, there are different technologies, but the first all-electronic was built here at Yale in 2009, I think. And we started with just 2 quantum bits. But before that, and continuing now, there is a Moore's law just not in the number of quantum bits, but in the length of time that those bits can stay coherent, that they can remember their quantum information. And that time has grown exponentially by about 6 orders of magnitude since the field of superconducting quantum bits was invented 20 years ago. And they're now working well enough that we can begin to do error correction. We can begin to scale up to larger numbers of quantum bits and the type of Moore's law that we're familiar with in terms of transistor count. I'm not sure we're have even invented the transistor yet. It might still be either the relay or the vacuum tube era, but we're, at the moment making progress, but still it's very early days.
So what's your take on the best applications for quantum computers today? Are they ready to solve real world problems, or are we still in the experimental development stage?
This is still an experimental development stage. Computer scientists like to classify different types of problems by their degree of difficulty. As you make the size of a database larger and larger, does the problem become exponentially harder or merely polynomially harder? And that problem of classifying how hard different problems are on a quantum computer is an open research subject in computer science. But there are certain areas that we know for sure quantum computers will do well. And one of the early applications will actually be solving physics and chemistry problems, actually building a quantum computer to solve the equations of quantum mechanics. So for example, if you're trying to design a drug molecule and you want to know how, a certain shape molecule binds to a certain pocket on a target molecule and how strongly it binds, you have to solve Schrodinger's equation that describes the energies of all the electrons, all the particles in the system. And that's provably a hard problem for classical computers. And it's known that quantum computers, if you could build sufficiently large and sufficiently accurate ones, they could solve such problems exponentially faster. So people are already doing very small calculations, hydrogen bonding to a helium ion, or two lithium atoms binding, things that are very easy for chemists to solve by ordinary means today, but we're practicing and learning how to do these things and how to write good algorithms for quantum computers in anticipation of better hardware.
So are there applications that traditional computers, or as you call them, classic computers, will always be better at, or is it just a matter of time before quantum computers take over?
A quantum computer can solve, is at least as good as any classical computer. There's no, you could operate them in a kind of classical mode where they would act like an ordinary computer. So there's no problem which a classical computer would be better at in principle. Now, in practice, classical computers are, have trillions of dollars have been invested in making them extremely fast and many parallel parts and so forth. So they're extremely high performance devices today. But in terms of extra powers that a quantum computer has, there are no deficits. It can, in principle, do as well as a quantum computer, a classical computer. Its clock speed might be slower or something, but there are certain problems that are provably hard for classical computers, which are easier for quantum hardware.
Dr. Steven Girvin, thank you so much for spending some time and get insight on error correction and quantum computing. And if somebody wants to find you, maybe they want to find out more about your work, how can they do that?
I can be reached by email at steven.girvin@yale.edu.
Thanks again for your time. And if you want to connect with me, you can. You can find more of my interviews right here on ZDNet or Tech Republic, or go to my website, tonyahall.net. I've got links to all my social sites, and I hope to hear from you. Thanks for watching.